Hi everyone, I'm Yang Zhengsha. This is my final project for Applied Deep Learning class in fall 2020, which is cancer detection in gigapixel pathology images. This presentation includes 9 sections. Deep learning models are commonly used in clinical studies for assisting purposes. The objective of this project is to build a model by leveraging deep learning models for cancer detection and localization in gigapixel pathology images. In real-world clinical studies, pathologists may have many patients, and the time for them to spend on each slide of the patient's tissues is limited. Also, mistakes may happen when a pathologist checks the cancer cells using a microscope. Thus, the development of a cancer detection and localization tool can help to assist physicians with diagnosis and prognosis on cancer. The models applied in this project are convolutional neural networks architectures. Now let's take a look at the dataset. The dataset used in this project is Chameleon 16, which includes 400 whole slide images collected independently from 2 medical centers in the Netherlands. The entire dataset takes 600 GB storage. Each slide image takes 1 to 3 GB. In my project, I only utilized 11 images. After converting images to appropriate format, each slide image is in TIFF format and contains 8 levels of resolution. Also, the labels of those slide images are stored as mask images, which contains the area of cancer cells. As shown in the mask image, the yellow areas denote the area of tumors, and in the overlaid image, the red areas denote the area of tumors. The images are read through OpenSlide, which is a C library that provides a simple interface to read whole slide images. Given a gigapixel pathology image, the goal is to classify if the image contains tumor and localize the tumors for a pathologist's review. Due to the large size of the slide and the limited number of slides, the solution to this problem is not to train a deep learning model using the original slide images and mask images as inputs. Instead, I will randomly extract smaller patches from the original image datasets at different levels as inputs. For prediction, I will perform inference over patches in a sliding window across the slide and generate a tumor probability heat map. This method is first proposed by paper detecting cancer metastasis on gigapixel pathology images in 2017. I will analyze the smaller patches at level 0 and level 2, which correspond to 128 and 32 magnification levels to the original slide images. Each patch has 299 square image size with respect to its magnification level. I labeled each patch as tumor if the central 128 square region has at least 1 tumor pixel. The 128 square region is according to the larger magnification, which is level 0. For train validation and test split, I split 8 slide images to train set, 1 slide image to validation set, and 2 slide images to the test set. To extract smaller patches, I first extracted all tissue pixels at level 7 as shown in the red regions in the sample image. Then I mapped the level 7 tissue pixel to level 0. After that, I checked whether the patches centered at those tissue pixels have tumors or not. If yes, I labeled these patches as tumor, which is class 1. The others are normal, which belong to class 0. After proper labeling, I stored the tumor and normal patches to NumPy arrays. For each level per slide image, I extracted 200 tumor patches and 200 normal patches for data balance. So the total number of patches at 2 levels for my entire dataset is 8,800, which includes 6,400 training patches, 800 validation patches, and 1,600 test patches. For the modeling part, I constructed 3 models, including 2 single-scale models at level 0 and level 2, and 1 multiple-scale model at level 0 and level 2. For single model data input pipeline, I used TensorFlow TF the data. I also did data augmentation for both single-scale models to reduce overfitting. The steps include horizontally random flip, saturation and brightness adjustment, and random rotation of 90 degrees. I rescaled the patches to range -1 to 1, with batch size 512 and random shuffle for train and validation sets. For a single model at level 0, my base model is transfer learning Inception v3 with all layers non-trainable. Then I added 1 dropout layer with rate 0.5 and 1 global average pooling layer to reduce overfitting. My prediction layer is 1 dense layer with sigmoid activation. I used ADM with default learning rate as optimizer, and binary cross-entropy as loss function. Since my dataset is balanced, I used default accuracy as evaluation metrics. I trained 15 epochs. The validation accuracy is around 78%, and the test accuracy is around 84%. For single model at level 2, my model construction is the same as the one at level 0. The only difference is that, for this one, I used ADM optimizer with a much smaller learning rate, which is 4 times 10 to the -4th power. The validation accuracy is higher than the single-scale model at level 0, which is around 81%, but the test accuracy is slower, which is around 80%. For multiple-scale model, I didn't do data augmentation because there are enough train samples. I also scaled the patches to range -1 to 1. I constructed the model with 2 subnetworks using transfer learning Inception v3. Each subnetwork has the same configuration as my previous single models. For better model performance, I adjusted the learning rate of ADM optimizer to 2 times 10 to the -5th power. Due to RAM limitation, I trained with default batch size. From the result, we can see that the validation accuracy is around 81% and the test accuracy is around 83%. By comparing two single-scale models, the validation accuracy increases from single model at level 0, and the test accuracy increases from single model at level 2. Therefore, among the 3 models, the multiple-scale one shows the best model performance. For visualizing model prediction and localizing tumors, I used the sliding window approach. To implement this method, I extracted all patches of size 299 square at the corresponding level of magnification as sliding windows to make predictions. To be more specific, for each patch extracted, I first checked whether this patch contains tissue pixels. If yes, I would run prediction on it and classify it to tumor or normal. Then I plotted the tumor patches to red color by creating a separate mask, just like the original mask image. I implemented predictions of all of my 3 models to one of the test images. Then I plotted the tumor probability heat maps. As shown in the slides, the first image is the original image with ground truth, and the other 3 are prediction heat maps generated by the 3 models. From the prediction heat maps, we can see that the heat map of single model at level 0 contains the most noise, whereas the one at level 2 contains the least noise. However, by comparing the large tumor clusters with the original image, we can see that the prediction of the multiple scale model has the least bias. Therefore, the heat maps also show that the multiple scale model has the best performance. The next section is code walkthrough. I worked on Google Colab utilizing GPU. There are 6 files in total, and I stored all the processed data on Google Drive. This one is the file of patches extraction. I used the starter code provided. I also wrote my own function of getting patches. Then I used this function to extract patches for train, validation, and test sets. The second file contains the two single model constructions. I did some visualization for patches and data augmentation. Then I trained models and plotted the accuracies. The next file is the multiple scale modeling. Due to RAM limitation, I rescaled the patches and then stored them in Google Drive. Then I trained the model. Similar to single models, I plotted the accuracies and a model workflow as well. The other three files are predictions of heat maps. I loaded the saved model in H5 format and then made predictions. The prediction methods are the same for all three models. There is an actual and predicted images comparison at the end of each file. Also, due to RAM limitation, the heat maps were plotted on level 4. Although the resolution is lower, the heat maps are still clearly enough to observe the prediction outcomes. In conclusion, among all of my three models, the multiple scale one performs the best. As we can see from the table, the multiple model has higher validation accuracy than single model level 0 and higher test accuracy than single model level 2. For future work, I expect to perform another multiple scale model with 3 or 4 levels. Also, I expect to utilize more slide images with more extracted patches as data input. Next, since Inception v3 is a relatively large transfer learning model, I expect to train other smaller transfer learning models like MobileNet, which requires less training time. Thanks for watching.